All right, howdy folks. Welcome to the Professor Carbon YouTube channel. In this video, what we're going to do is go over kind of an unusual hydrolysis of a lactone. And so remember, a lactone is the name given to a cyclic ester, and so we definitely have an ester functional group here. And it is part of a ring, and so we'll call that a lactone, and here we have a base hydrolysis. And so a fun thing about this is actually called nepetalactone, and it's the key ingredient of catnip. And so it's kind of a fun molecule to consider the structure of altogether. There's one particular trick to this, though, and that is we're going to get an aldehyde out. And if you notice here, we have a trapped enol ether. And so enol ethers are not your typical ether, because they represent trapped aldehydes and ketones instead of alcohols coupled together. So as with all these videos, what I encourage you to do is actually to take a pause here, try to work through this mechanism all on your own, and then come back and watch what the answer I provide. So please do that right now. All right, welcome back. What I'm going to do here is just talk through kind of the basic of this mechanism. In general, we could start this as any old acyl substitution mechanism, just like hydrolyzing any old ester. So let's just start with sodium hydroxide. So Na plus, and then we have OH minus. I'm going to take that minus and do my attack on the carbonyl oxygen. So that then will get me to here. So that works out quite nicely. And the thing I really like about the acyl substitution mechanism is the other name we give it, addition elimination, tells you exactly what you need to do. So here we've added our nucleophile. The next step then is to eliminate a group. And so we're going to take that, swing it on over, and kick off O minus. And that would give us what we have here. Now, this is technically an enolate, and anytime I draw a intermediate that I'm familiar with, I always try to name those. So enolate, so I like that. And enolates are quite basic, and here we have a carboxylic acid, which is quite acidic. And so we could take this and use the enolate double bond here and deprotonate, and that would actually get us all the way directly to the product. And what I like about that is if we count, this is the reactive carbon, so that would be 1, 2, 3, 4, 5, 6. So it's a nice 6-membered ring that would be doing that deprotonation intramolecularly. And so that would be quite all right as a pathway to get there. Nice 3 steps. Now, if you don't like that intramolecular deprotonation, there are a couple of other potential mechanisms that you could draw as well, that if I were grading these, I would accept for full credit. One of those, and I'm just going to redraw the same intermediate here, because this is going to be the point where we diverge. So if you didn't get to here, we have a little bit of a problem. But as long as you got to there, there's a couple of different ways to complete things. So one thing is, we've generated a pretty good acid in the presence of this carboxylic acid, and it's really hard to tell how much hydroxide is around. So what happens if we just deprotonate that, and then we can so we could have a dianion. Now, typically the second pK is uphill a little bit from the first pK, because we don't want to put 2 negative charges too close together. And so, it's probably okay here. Carboxylic acids are quite acidic. Sodium hydroxide is quite basic, and so that would probably work out. This would then generate some water. And so then we could imagine the enolate deprotonating the water in an intermolecular fashion. And so that would get us to the product as well. The one things you don't want to do is have anything with O+. So anything with the positively charged oxygen is definitely going to be bad in this mechanism because we're starting with our hydroxide, and anything with a carbocation is also going to be bad. So regardless of what mechanism you choose and exactly how you do the proton transfer, and there can be some ambiguity there with, especially for, it's not really clear if water is the proton shuttle, if this thing deprotonates intramolecularly. That would all be okay, especially if it's a nice 6-membered ring. The one thing you want to avoid is anything with positively charged oxygens in it. That's for sure going to be a problem. All right, that's it for this mechanism. All in all, I thought it was just fun because it goes back to a molecule that many of us have encountered in everyday life and may not have realized the specific intricacies of. So thank you for following the Professor Carbon YouTube channel. Please do subscribe.